Task 6 is actually taken directly from the lecture. So we have already done this in the lecture, but because it wasn't much clear, so we are doing it again in the tutorial. Now, we have a hypothetical computer that stores 9 bits of information to represent real numbers. First bit is used for the sign of the number. The second bit is used for the sign of the exponent. 3 bits are used for the magnitude of the exponent and 4 bits for the magnitude of the mantissa. Represent the number 13.6 in binary using the floating point representation. And how would the number be represented in the computer? So start working on this. Let me first draw the placeholders or the way you will put the number in the floating point representation. So you have here for the first one, for the sign of the mantissa, and the next bit will be for the sign of exponent, and then you will have 3 bits for the exponent itself, and then you have 4 bits for the mantissa. Now, the first task of us to represent the number 13.6 in binary. So we can first represent 13.6 in binary. And first, as we have seen in the task 1, we'll first take the number 13 and we'll represent it in binary. So we have 13 and the quotient and the remainder here. 13 divided by 2 is 6 here, and 1 for the remainder. 6 divided by 2, we have 3 and 0. 3 divided by 2, we have 1 and 1 as the remainder. Then we have the 1 divided by 2. We have 0 as the quotient and 1 as the remainder. So once we reach 0, we stop, and for the remainder we take it bottom up, and we have here 1 1 0 1 for the 13. So we have here 1 1 0 1 in base 2 for 13, and then we go for the 0.6 to convert it to binary. So we have 0.6 times 2 is 1.2, and we'll only take the integer part and write it here, and then we have 0.2 times 2, which is 0.4. We take the integer part and write it here down, and then we have the 0.4 value here, so that's 0.4 times 2, which is 0.8, and we take the integer part and write it down here. We take the 0.8 now again, multiplied by 2, which gives us 1.6. We take the integer part and write it down here. We have 0.6 left here into 2, which will give us 1.2. So we just take the 1 and we have to continue this. Okay, but then we know that for the Mantissa we are only given actually 4 bits to store, so we'll just take 4 bits from here, but we'll now take it from top to bottom. So we can take here 0.10001. So we could stop here now, and the rest of the numbers we don't need to write down. So 13.6 in the base 10 will look like 1101.1001 and more in base 2. Now to put this in the floating point representation, so let's write it down now. Put it in floating point representation. We will have, first we need it like 1 point something, so we have to take this the radix point here, so we'll have now 1.1011001 times 2 to the power, because we move the radix point 3 steps, so 2 to the power 3. And of course we have to convert the 3 now, which is in base 10, to base 2, which is 011 in base 2. So we can write this down as 1.1011001 times 2 to the power 011. So that's the floating point representation of 13.6. Now for the second part of the question, which asks how would the number be represented in the computer. So let's work on that part now. Computer representation of the number. Would be like as we wrote at the top here. So we have first bit for the sign of the Mantissa. The sign of the Mantissa here is positive, so we make it 0. Then the sign of the exponent here, which is 3, is positive 2, so we write it as 0. And then the sign of the exponent, or no, so not the sign, but the exponent is 011, so we'll write that down here. And then we have the Mantissa, but in the Mantissa we can only fill 4 bits, so we'll take the first 4 digits, which is 1. Okay, it's after the decimal, so we will take from 1011. So we have 1011. So this is how the computer will represent the number 13.6.